Hi, this is ET370 Lecture 3, and this is going to be a three-part lecture today. The first third, we're going to go over half-wave rectifiers. We'll talk about how they work, look at how would you pick a capacitor to smooth the output, and look at this thing called the peak inverse voltage, which is a way to calculate the worst case scenario for the diodes. In the second and third part, we will go over a full wave rectifier and a three-phase rectifier. I forgot to mention, we'll also look at a circuit sim to just kind of tie it all together. All right, so let's begin. So a half-wave rectifier, well, actually all of these will convert AC to DC, right? So you have your AC oscillating signal, and you want to now have it rectified, smooth, in a DC waveform, okay? And the idea is it's going to remove the negative part of the AC input, right? So the AC input goes positive, negative, and this kills the negative. And we smooth it with a capacitor at the output because the output will be bumpy without a capacitor. And so here's an implementation of a very simple half wave. So imagine you have your AC input here, you have your diode, which only allows one-way current. You have a load resistor, this could be a light bulb, a charger, whatever you want to actually power with DC. And then you have a capacitor here that will smooth all the bumpiness of the output from this diode. Okay. And so these are all just the terms defined. Imagine, we have our friend, the VP cosine omega t, that's our AC mathematical equation for this. This is the rectified output voltage V naught. We're going to assume an ideal diode. In practice, of course, it has some forward voltage, load resistor, smoothing capacitor, and the load current, which is the current in this resistor. Okay. So let's look at this very quickly without a capacitor. So just the half wave here. And we've done this before in previous lectures, right? If this voltage here is positive, this diode's going to be in forward bias. And if this voltage is negative, this diode will be in reverse bias or off, right? And so here's a plot showing the input voltage as a function of time. And the dashed line here is what the output voltage would look like under normal operations without a capacitor. And so you can see that in this time interval, the diode is in forward bias and it's acting like a short. So this is acting like a short by KVL. These two voltages would be the same. And you see that the dashed line and the solid line follow each other. In other words, V naught matches VI. Now in reverse bias, when this guy is negative, when you have high pressure down here, what happens? This diode is blocking, it's in reverse bias, and this output just becomes zero, and then the pattern repeats, okay? So without a capacitor, so V naught is positive, but not smooth, right? So you can see that positive, but not smooth. You get these bumpies, and here it's just zero, okay? So if we add a capacitor, let's see what's gonna happen. Now, what does a capacitor do? Remember, a capacitor is like we have our flexible membrane, right? It's charging up and then discharging. And so you can imagine during these positive segments, right, where this guy is positive and this guy's acting like a short, now the current's going to flow in here into the load resistor, but it's also going to flow into the capacitor, right, and charge up that capacitor. And so you're getting this kind of behavior right here. See, VI is going to provide power into the load and into the capacitor. And then what's going to happen? When this guy, there's going to be a point at which this guy shuts off. And during this time, the diode is going to be in reverse bias. And the capacitor is going to provide energy into the resistor, right? So this is going to do the work while this diode is turning off. Okay. And so what you're going to get is you're going to get this smoother output voltage, right? You see this dashed line representing the output voltage here with the capacitor. So this guy charges up the capacitor and provides current, the input does. And then once this diode shuts off, what happens? Now the V out actually doesn't drop down to zero anymore. It actually slowly decays at the time constant of this capacitor resistor setup, right? And then charges again, and the pattern repeats, right? Okay, so V out is smoother. It's not perfect, but it does have some ripple. And so the ripple voltage is defined as this peak minus the ripple, right? So that's the ripple voltage is this peak minus this trough here, okay? Now the average voltage, right, the true average V out is approximately this peak minus half of the ripple voltage, and I wrote that here, right? So the average output is equal to this minus this peak minus half, okay? All right. Now, let's say you want to choose the capacitor. How would you actually pick this capacitor, assuming you know the input and the peak, and you know this resistor and the desired load and the ripple voltage, or the acceptable ripple voltage? Well, it's actually from this equation. C, the capacitance, equals this load current times the period, which is actually the period of oscillation here, right? The time it goes from peak to peak, divided by an acceptable ripple voltage, okay? And so you can see all the terms defined here. And maybe a question you might have is, well, where does this equation come from, right? It just seems arbitrary, pulled out of the hat, right? So let's imagine that the charge that's removed from one cycle can be computed. In fact, we can actually use this equation here. And so this is just saying, this is basically the definition of current, right? Current is charge per time, right? Or I've just rearranged it, charge equals current times time, right? Coulombs per second, seconds, you can see the dimensions cancel. Okay, so that means the current exposed to one period of oscillation here is going to tell us how much charge was removed in one cycle. And we can equate that charge to the definition of capacitance. So the definition of capacitance is the charge is equal to the voltage across the capacitor times its capacitance. And look at this, we have Q and Q, and we can say, well, if this charge is the same as this charge that the capacitance can hold, then we can equate these two and see we have one equation, one unknown. So C equals ILT, the period over the ripple voltage, okay? And that's how you get this. Now, how do we use this equation in this example? So we would figure out what is the acceptable ripple voltage, right? So we could pick it, I don't know, 5 volts, 1 volt, half a volt, and we can figure out, well, what's the frequency? So if it's 60 hertz, it's going to be 16 milliseconds. And we could look at, well, what is going to be the average current that we expect? And that's roughly V out divided by R in this case. Okay, now it might be more complicated if you have a more complicated load. And those three things give you a starting point for computing this capacitor, right? Now, this is just a starting point. When you do it in practice, you might have to tweak the value, right? And that can be done through simulation. But this is a nice starting point, okay? Now, when you're designing these things, you also want to look at the diode. How would you spec the diode appropriately, right? Because the diode, you want to make sure it doesn't break on you. And so the thing you might want to look at is called the peak inverse voltage, okay? And so the peak inverse voltage is the voltage, the worst case voltage that this guy can handle under reverse bias, right? We don't want it to break down here. Okay, so let's look back at our half-wave example. Okay, so we have our situation here. Let's assume everything is roughly smooth, like this is nearly constant, but this guy is oscillating. Now, what is the worst case? The worst case here is when this is either plus or minus V peak, right? At the top or the bottom here, right? Plus or minus V peak. So the worst case reverse bias setting is when this is actually negative V peak, right? And so I'm just going to put a hard negative V peak constant voltage here. I'll put the diode voltage here, and I'll put the constant V out, because our desired is that this is actually V peak, right? Now, I can do a simple KVL, right? So this KVL, what do we have? Minus negative VP plus VD plus VP equals 0. And I can solve for this worst case V diode. And you can see here, it's not V peak, it's 2. It's actually minus 2 V peak. So in other words, let's say this was 100 volts going up and 100 volts going down. This diode needs to handle 200 volts, right? And so before you even connect it, what you'd want to do is check your data sheet of your diode and make sure it can handle twice the amount of voltage that the input is providing in this half-wave rectifier case, okay? So depending on the circuit, you might have to do your own peak inverse analysis if you have a different circuit, but this is just for this half-wave rectifier example. Okay, so let's look at a circuit sim example where we're going to run some numbers and actually verify it on the simulation. So let's say this V peak, so it is going up to 100 and goes down to 100. And this is 100 ohms. So we have 100 volts peak and 100 ohms for the resistance here. And so the load current is going to be about 1 amps by Ohm's law. But let's say we have an acceptable ripple voltage of about 10 volts. Okay, it could be 5 volts. We just picked a number here, for example. Okay, the average voltage is going to be 100 minus V ripple over 2, which is going to be 95 volts. Okay, and then we can calculate the average load current, which is just going to be 95 divided by 100 by Ohm's law. Okay, now let's assume this thing is oscillating at 60 hertz. So that means the inverse of 1 over 60 is going to be 16 milliseconds or 0.016 seconds. And we can now use that capacitor equation, IL period over V ripple. And all the numbers are here, 0.95, 0.016, and the 10 from here. And the number we get is 16 millifarads or 0.0016 farads. And what we can now do is check the circuit sim and see if we get the nice behavior. Okay, so I'm going to switch over here and share screen with the circuit sim. And so what do we have here? We have, I'm going to actually open this up and run this. I'm going to run it right now without the capacitor. You can see I've been running it with the capacitor, but notice when I run it without the capacitor, I have my input voltage here and I have set to 60 hertz with 100 volts. Okay. And if I do the inverse, I get 16 milliseconds. And if you see on the output, the red line is going to be this output voltage across the resistor. Notice it's doing that half wave behavior. The green line is actually the input, and you can see the input's oscillating between positive and negative 100 volts. Okay, the diode is doing its action, right? It's blocking and then allowing current flow. You can see the current here plotted positive, negative, or positive, zero, just like the voltage. Okay. Now, if I close this capacitor, connect this capacitor in, if you look at the yellow dots here, you can see that when this diode is turned off, notice how the capacitor is delivering current, right? So you can see now this red line is now the new output voltage, and it is smoother than the original one. Okay. And so we also ran through the calculations here for the peak inverse voltage, and notice I'm plotting it, and notice the voltage here is at minus 200 volts. So this thing has to handle negative 200 volts and in the worst case. Now the average V out, I had the same equations, 100 minus, let's say the V ripple was 10, right? The acceptable V ripple. So that means the average V out is 95. And that would be the center of this red line here. Okay. The Ohm's law would say that the average current would be 0.95 amps, right? If I take the 95 over 100. And if we look at here, I'm plotting the average of the current, and it comes out to be 946 milliamps or 0.946. That's pretty darn close to 0.95 amps. And then we ran it through the capacitor equation, ILT over V ripple, 0.95, 0.016 over 10, and we get 0.0016 farads, and that's what we put into this capacitor. And you can see we're getting the behavior that we desire of 0.95 amps and a V ripple of about 10 volts. Okay. So I hope this simple half-wave example highlights a nice practical behavior of the diodes, and how would you choose a correct diode and a capacitor to smooth it out with a desired ripple voltage. Okay, I'll put the link to this simulation, so you can always click it and then check it in the description. So I hope this helped, and see you in the next lecture.